So this afternoon, our first talk is Francesca Carocci. And she is going to tell us, this is talk number 1, she's going to be telling us about the geometry of moduli spaces of stable maps to projective space and modular desingularization via log blowups.
I realize that it's a very long title, and hopefully it's explicative. Let's see if it's true that I managed to cover in these lectures as much as I said in the title. Anyway, thank you, the organizer, for the invitation. It's the first time I give a lecture series on Zoom. Let's see how it goes. So I have pre-written the notes because my handwriting is already bad enough when I'm concentrating just on writing. So I did that ahead, and we'll slowly go through the notes together, and please ask questions whenever you want. Okay, so what are the goals of this series of talks that I'm gonna deliver? So first of all, we want to understand the local and global geometry of the modular space of maps UPN, which means that we want to study the deformation theory of these modular spaces, look for local equations, describe their reducible components. And also we want to use this example of stable maps in genus 1 and genus 2 as an excuse to look at how to exploit ideas and techniques coming from log and tropical geometry to resolve singularity of the modular space in a modular fashion, which means in such a way that the resolution itself is a modular space. And this is what we're gonna talk about in the second half of this series of talks, also because we want to wait for Liana to develop the toric geometry language, and then we will build on that. So why should you care? Why should you care about this type of things? Well, on one hand, if you are an enumerative geometer and your goal is to compute invariants, say, for example, Gromov-Witten invariants, although we have been studying modular spaces of maps for 30 years now, actually it's very hard to compute this invariant as soon as the genus is bigger or equal than 1, and moreover, the meaning of these invariants is often unclear, in the sense that we would like to be computing genus G curves inside our projective space, but what we are counting are usually genus G curves together with lower genus curve. And the reason why this is happening is because, as we will see in many different ways, this modular space is very singular, and it has many components which parameterize the generate object. And if instead we manage to move our computation on a desingularization, first of all, these are going to be more accessible, and second of all, we are going to be able to define invariants with a better enumerative meaning. And if instead you do not care at all about modular space of maps, which is fair enough, I just want to convince you that log techniques are in general useful to study compactification of modular space. The motto is that log geometry controls the generation, and so is suitable to study compactification, and usually helps to cut down the number of components of a modular compactification, and so to give us minimal compactification. So techniques similar to those that we're going to see in this series of talks are also useful to study compactification of modular spaces of abelian differential or of K3 surfaces, or compactified Jacobian, or in general to study birational geometry of moduli of curves. Okay, so let me start with the first definitions and example. We'll start very slowly. Let me remind you that an n-pointed genus G pre-stable curve is a projective connected reduced curve which is at worst nodal, together with the choice of n distinct smooth points, which are called markings. And here is a cartoon picture to fix an image of in your mind of what a pre-stable curve should be. And the family of pre-stable mark curve over a scheme S is just a flat morphism pi from a scheme C to S together with n smooth section such that each fiber is a pre-stable curve. And here again, a cartoon picture to fix in your mind as a one parameter family of pre-stable curves look like. And let me also remind that given a pre-stable curve, we can associate with a combinatorial object, namely its dual graph, which consists of two sets, one of vertices, one of edges, and actually three sets, vertices, edges, and legs, together with the function from the set of vertices to the natural number, where the vertices are in one-to-one correspondence with the reducible component of our nodal curve, the edges are in one-to-one correspondence with the nodes in our curves, and finally the legs are in one-to-one correspondence with the markings. And the genus function just decorate the graph with a number which correspond to the genus of the reducible component. And here again, one example to fix ideas. So here we have these two nodes, which are going to correspond to these two edges. Here we have this other node corresponding to this one. We have marking only on one component, which are these infinite edges. And finally, we have a vertex for each component. And this is going to be useful later to describe combinatorially certain operations on pre-stable curves. And let me also define what is going to be one of the main characters of this series of talks, namely what is a stable map. A stable map with target X consists of the following data. We have an n-mark pre-stable curve C that we have just defined, together with the morphism F from C to X, which satisfy the following two conditions. If we have a component D in C, which is rational, and such that it is contracted by the curve, so the image of our rational component is a point, then we ask for the number of mark points on D plus the number of nodes on D to be at least 3. And if instead we have a genus 1 component which is contracted, then we ask for the number of mark point plus the number of plus the number of nodes to be at least 1. And in general, we'll just say, we will just say that this is the number of special points. So when in future, I'll say number of special points is just the number of these two. And these two conditions here are the stability condition on our F, and they ensure that the automorphisms of F are finite. And you can now imagine that a family of stable map is nothing but a flat family of pre-stable curve together with a map to X times S and n smooth section, such that every time we look at the fiber around over a point, we get a stable map. Actually, from now on, we only consider as a target the projective space. And we will say that our map has degree D if, when we look at the push forward induced in homology from the curve to the projective space, the image of the class of the curve is D times the class of a line. Or if you want, another way to think of it is that generically, when we look at the image of our curve inside the projective space and we intersect with the line, this is D points. So H is a hyperplane in PR. And since we are always going to look at maps to projective space, let me recall the following basic fact that is going to help us give example. When the target is the projective space, we have an equivalent way to think about maps. Giving a map to projective space is the same thing as giving a line bundle of degree D on our pre-stable curve, together with R+1 section of this line bundle, which do not vanish simultaneously. In fact, once we are given this section, we can define the map as the evaluation in these sections, and the fact that they do not vanish simultaneously is what ensures us that the map is well defined. And we can rephrase stability.
Francesca?
Yes.
May I ask something?
Sure.
Should I assume that this is sort of true for any projective variety, not just PR?
No,
when
this
the target.
No, this is true. I mean, this is true for toric variety. There is a generalization of this. In general, when one is giving a map to a toric variety, is the same as giving a bunch of line bundles and a bunch of sections of these. It's not true for any toric variety, because in general, say for example, for any projective variety, say for example, your projective variety is an hypersurface in the projective space, then you want the image section to satisfy the equation of that hypersurface. So there is some constraint on these sections.
Thank you.
Okay, and we can rephrase the stability condition as the ampleness of this line bundle, the canonical of the curve C twisted by the mark point and by the second power of my line bundle L. Okay, so let's see a few examples. How do this table map look like? So let's start with two very easy examples. First, we start with the simplest curve of them all. C is P1, and we choose as line bundle OP13. And let's take a section, this fourth section, which is actually a base for H0L. And let's look at the map the map defined as evaluation in this section. Well, you can easily see that this is nothing but the embedding of P1 in P3 as a twisted cubic. And we will see that this is a point in M00 P33. P33, yes. Okay, so this is a nice map, it's an embedding, and let's see another example of a nice map. Let's take our curve to be a smooth genus 1 curve, and let's choose a point on it, and let's take as line bundle O of 3 times this point. Then let me remind you the following fact. The H0 of this line bundle has 3 sections, S0, S1, S2, which do not vanish simultaneously. And if we consider the map defined via evaluation by these sections, this is nothing but the embedding of this smooth genus 1 as a smooth cubic in P2. So the image is going to be a curve which satisfies an equation like this, where A and B will depend from the elliptic curve, so from its J invariant. And you can see that the point P is mapped to 0, 0, 1. If you want details of this example, you can find them just in Action Algebraic Geometry in the chapter about curves. So this is again a nice map because it's an embedding. So let's see some other example. Let's now start from curve, which is a genus 1 curve with a node. And let's look at a line bundle, which is the trivial line bundle when we restrict it to the elliptic component, and is again O3 when we restrict it to the P1 component. Then what are the sections of this line bundle? Well, these are just the section on the normalization C tilde. So the section of the trivial line bundle on E and the section of O3 on P1, which coincide at the point Q, so which take the same value at Q. And let's choose, for example, this 3 section, where here on the left column I'm writing down the value of the section of the constant section at the point Q, and here on the right column I'm writing what is the section on P1, and you can check that I've chosen them in such a way that the value coincide at this point Q. And what happens if now we look at the map defined by evaluation in this section? Well, what's happening is that the curve, the elliptic curve, is contracted to a point, specifically the point -1, 0, 1. And instead, the image of P1 is the nodal cubic with the equation zy squared minus x cubed minus x squared z equals 0. And you can see that the point where the elliptic curve is contracted is actually not the singular one, it's just another point in our curve. And if we look at the map from P1 to its image, this is just the normalization, because on P1, these 2 branches are being pulled off. And this is an element in M10 P23, and we will see that this is a singular point of this moduli space. And finally, let me do a last example. In genus 2, we consider a curve which is the union at a node of a smooth genus 2 curve and a P1 again, and we consider a line bundle which is the canonical bundle of the genus 2 and restricted to it, and it's just O2 on P1. So in total, so this line bundle has total degree 4. And let me recall you the following fact. Every genus 2 curve admits a map to P1, a 2-to-1 map to P1. Namely, every genus 2 curve is hyperelliptic, and this line bundle omega z is nothing but the pullback along this map of the O1 on P1. And the existence of this map tells us that this omega z has 2 global sections, U0 and U1, and we can choose them in such a way that U0 vanishes at the node Q and U1 instead doesn't. Then let's take a section of H0L, then once again are the section which glue these 3. Once again, they've been chosen in certain, this coefficient here is just to make the gluing possible, it's some number. And if I now look at the image of my map, what I obtain is the union of a smooth quadric, is the P1, which is being embedded as a smooth quadric in P2, and a line, which is the image of the genus 2 curve. And the map from the genus 2 curve to this line is this 2-to-1 cover we said before. So it's a finite cover. And essentially, these are this example that we have seen, these are the building blocks of stable maps. Any stable map are going to have some components that are contracted, some components which map as a finite cover on their image, and some components which are embedded. Okay, so these are all examples of points in this modular space of stable maps to projective space, which we have also rephrased as the modular space of curve, line bundle, and section. But if we really want to understand the structure of this modular space, what we need to understand is how the points fit together in families. So to begin with, let us study the easiest possible family, the smallest possible family, namely the families over fat points. So we start by studying family over a point which is just spec ct mod t to the n, where we have only one close point, which is spec c. And if you really would rather not think about non-reduced schemes, I feel you can think that SS0 is a germ of a complex manifold. But it's not too bad thinking about this gadget as well. And in fact, we are mostly interested in two things. We want to understand deformation over what are called the dual number. So this is really just, if you want to imagine it, imagine that there is a point together with a tiny direction. And also we want to understand when, given a small deformation over the epsilon, we can extend it to a deformation over a larger base scheme. For example, over spec ct t to the n with n bigger than 2. And why are we interested in these 2 points? Well, because the set of deformation over the epsilon is going to tell us what is the tangent space to the modular space around the point we are looking at. And the presence of obstruction is what is going to tell us that the modular space might be singular. And let me draw a cartoon picture to illustrate these 2 concepts. Suppose that our modular space looked like another curve. This has nothing to do with another curve we saw before, nor to another curve we see later. Usually we think of a curve as a point in our modular space. Instead here, I'm saying imagine the modular space looks this way. And suppose that we are looking at deformation of the point P. Then, in this case, the deformation over the dual number are nothing but the homomorphism which from d epsilon to m, which maps 0 in P. And this is a 2-dimensional vector space, and is nothing but the Zariski tangent space at the point. But you can see that when we choose a tangent direction, we cannot follow this tangent direction forever, staying in M. And the reason is that these many directions are obstructed, and this is because this is a singular point of our modular space. And in this very specific example, the obstruction are contained in the one-dimensional vector space given by the homomorphism from the ideal of the modular space in A2 to the point. What does this mean? It means that there exists a map which is called the obstruction map from the set of deformation QV, such that given a deformation, this lifts to a deformation over a larger base if and only if the image of this map is 0. And the fact that this is one-dimensional is what tells us that the dimension of M is equal 1, because you should think that the dimension of the obstruction space is equal to the number of equations of M in a smooth ambient. And now we are going in the rest of the talk, we are going to study the deformation we are interested in. And so before studying the particular deformation we are interested in, I'll probably stop here and we can take a 5-minute break and you can ask me questions on what I said so far.
Okay, can we pause the recording briefly? Is Ollie there? I still see recording flashing.
I think I can also pause the recording. Should I do it?
I'm not sure. I'm not sure if I want to mess around with it just in case.
Okay.
Just in case it breaks something. Maybe she's dealing with something briefly.
You're worse than my grandma with the remote control.
Well, anyone who doesn't mind appearing on the video can ask questions.
Sorry, yes. Why can't we follow any of the tangent directions any longer from the picture? I didn't quite understand that.
Because, so here the tangent space is all of C squared.
Yes.
It's C2. But I mean, we have the modular space is on a curve. So if we look at one direction, which is not, let me zoom in here.
When you say here, it's around that point, right?
So around, the curve looks like this, but we have tangent direction going this way.
Yes.
So, but this is, I mean, this is an algebraic fact. This is the equation of the modular space.
Mm-hmm.
And the point is that y minus x starts being in this space, but then it stops because there is no, here I have, my modular space here does not exist. The only two direction, let me do it cleanly. So this is my curve. And how do I give you, this is the equation. And how do I give you a tangent direction? I have to give you a map from C epsilon mod epsilon squared, a map from Cx y mod y times x into C epsilon mod epsilon squared. This is just the dual of what I wrote here in terms of variety. And what I can do is enough to go, epsilon goes to a epsilon and y goes to b epsilon for some a and b in C.
Mm-hmm.
And this is what telling me that the tangent is C2. I noticed that this satisfies the equation x times y equals 0. But if I am now, instead of here, I am C epsilon mod epsilon cube, the equation x times y equals 0 is no longer satisfied unless one between A and B is 0, which is telling you that the only two directions you can follow are either this one or this one.
Okay, yeah, that makes sense. Thank you.
More questions? Are we all doing fine?
Should I leave it or should I delete it, this bit?
I think it's fine to leave it. I mean, it doesn't obstruct any of the rest of the notes. So,
okay.
If people think it will be helpful potentially to them if they're looking back at this, it's.
I mean, is it that you're going along sort of the curve in the moduli, when you're moving in the moduli space, you're going along the curve in the direction that the tangent vector points you towards, right?
Yeah.
And as soon as you arrive at that singular point, you don't know where to go anymore. Exactly.
More that I cannot go anywhere the tangent vector point me towards.
Mm-hmm.
I kind of get trapped. There are some direction towards which I can go, but other where I cannot follow. I get trapped into the singular point.
Mm-hmm. Okay. And in general, did you say that this can have components of different dimensions or not in this case?
So this is, in this example,
this is an easy, I guess, idea.
In this example, which is just this cartoon example, there is one component, which is the curve itself, and I have just this singular point. But you can have modular spaces that, for example, look like this,
mm-hmm.
a plane and a line. And here, for example, you have two components, and you don't even have a well-defined notion of dimension, because the dimension, if you are here, is going to be 1, and if you're here, is going to be 2, and if you're here, you're going to say you're going to say
you're stuck in the point again.
Yeah, you're going to get stuck in the point again. In general, the fact is that when I look at the tangent space to a point, if that point is smooth, then the dimension of the tangent space is equal to the dimension of my variety. But if the point is singular, as we saw in this example, the tangent space is going to be bigger. And usually, in the singular points, you should think that the actual dimension of the space is the dimension of the tangent space minus the dimension of the obstructions. Okay. Shall we resume?
Yeah, we've had 5 minutes or so, so.
Okay, let me just drink some water. Okay. So, first of all, let's have a look at the formation of a curve. So C is a curve, and we're looking at flat families over fat point. So, and this is a theorem, this is a classical theorem. You can find all of the details of the proof in either the book called The Formation Theory by Arshen, or The Formation of Algebraic Schemes by Cernesi, or the Arbarello-Cornazba-Grifty books on curve. And the first statement is the following: if C is a smooth curve, then the deformation over, that didn't have to disappear. The deformation over the dual number are classified by the H1 of the tangent, sheaf of the curve, which I remind you is just the dual of the sheaf of differential or canonical. So let's see, how do you prove such a statement, just to have an idea of how this works. We have to give something for granted, but you can find also this in the reference I've told you before. And what we give for granted is the following, is that if U is an affine scheme, which is smooth, then every deformation over the dual number is trivial, which means that it's just isomorphic to the product deformation U times the epsilon. So now let's choose a cover, an affine cover for our projective curve, smooth curve C. And let's look at one deformation over the epsilon. This deformation over the epsilon is going to induce the formation of the affine UI. And for what we are taking for granted, we know that the induced deformation over the UI are all trivial. So we have a series of isomorphism phi from this induced deformation to the trivial one. And thus, if we look at double intersection, we find automorphisms. And these automorphisms are the identity when restricted to epsilon equals 0, which tell us that actually over a point of the form B0 plus epsilon B1, which is how the point in this trivial deformation look like, the automorphism take this simple form, is B0 plus epsilon times B1 plus some additive morphism theta, EJ. And imposing the fact that psi is indeed a morphism of rings, so imposing this condition, you can check that this morphism theta ij are local section of the tangent sheaf. They are, so Tj are derivations if you want. And moreover, one can also see again from the definition that they satisfy the co-cycle condition. And what it's telling us is that this collection of theta ij is giving us an element in the H1 of the tangent sheaf on C. And now if actually we do reverse engineering of this argument, we see that given such an object, we can get a deformation gluing the local trivial deformation using the Pij defined as the identity plus epsilon B1 plus theta. Okay. So this was for smooth curves. What instead when C is nodal? Then in that case, the first order deformation are parameterized by the group of extension of omega C with OC. And notice that when C is smooth, this vector space is nothing but the H1 CTC. And this vector space actually has a natural splitting in two components. One which is indeed the H1 of the tangent sheaf, and the other one which is the H0 of the local extension. And the H1 of the tangent sheaf also in this case parameterize some deformation. Which ones? The ones which are locally trivial, and the proof is exactly the one we have just given. Instead, this other part, in this vector space, one can see that it has dimension equal to the number of nodes of the curve C, and this parameterizes deformation which smoothen the node. And we're going to see in a second what this means. I mean, I can say immediately, if we have, what this means is that locally, if we have our node, this parameterized deformation of the form xy minus t equals 0. So when t is different from 0, this means that we have some smooth curve. Another thing that it's important for us to know is that there are no obstruction to lift the formation of nodal curve. So this is good. This is going to tell us that when we're going to look at the modular spaces of curves, that we expect it to be smooth. And finally, the last thing that I want to say is that the infinitesimal automorphism of the curve, namely the tangent to the group of automorphisms at a point, is given by the H0 of the tangent sheaf. Okay, and let's see what can we say now that we've studied this deformation of curves about the parameter space of all curves. Before we do that, let me notice one thing. The dimension of this group of extension can jump as we choose different nodal curve of genus G. For example, if it jumps if the C is smooth or the C is nodal, these are different, can be, but their difference is constant, and it is once we fix the genus and the number of the markings. And this is going to be what will give us a well-defined dimension. And before I go ahead, let me just quickly say that this is for the formation of curve without marking, and instead, if we add markings, so we have C, but we also can move around the P1, Pn, then this is parameterized by Tc twisted by minus P1 minus Pn. And also in the singular case, this only affects this component, and is H1 C minus P1 minus Pn. And the presence of markings also affect the automorphism. So this becomes the H0 of Tc shifted by the marking. Okay, so now let's look at the moduli stack of pre-stable curves. So we have this space parameterizing all the pre-stable marked curves. What can we say about it, having studied the deformations? So we have seen that the tangent space is given by the x1 of I've written in this way, omega twisted by the marking OC. And notice that if the dimension of the automorphism is 0, so if we have no automorphism for our curve, or we have only finitely many, then we expect this to be the dimension of MGN at C, because we said that there are no obstruction. In general, instead, the dimension is going to be given by this Euler characteristic, because we, in order to compute the dimension, we have to take into account the automorphism as well. So you can compute that this is just 3g minus 3 plus n, which is probably something you've seen before. And as we have already said, this space is smooth. The fact that there are these automorphisms and that there are possibly infinitely many of them is what tells us that this space is not quite a scheme, but is an Artin stack. But we will not worry about this technicality for the following reason. If we look around a point C in our modular space, we can always choose a scheme U together with the smooth map from U to our modular space, which we call a chart, and describing the stack around our point C just means to describe this scheme U. And this small lemma, which is just a lemma of commutative algebra, will tell us how the modular space look like in this case of curves. So we have that exists a unique local complete C algebra, which is smooth of dimension m, which is just the complete algebra in m variables. And what this is telling us is that locally analytically, the chart U just look like an affine space, essentially. And we will distinguish those coordinates in the affine space which correspond to the k nodes of our curve C around which we are looking. And these are what are called the smoothing parameter of our curve. And essentially, this is what I already said before. If we now look at the universal curve over this chart U, which means is that family of curve such that any other family is pulled back from this one, then if C looks this way with some node Q1, Q2, Qk, then our curve C around these points has equation x, y, y, y minus ti equals 0. So we know U look like, we know how the universal curve over it look like, and this is as much as one can hope for a modular space. And let me say once again that we will never again worry about stackiness issues, and will just take into account automorphism when we need to compute dimension. This means that every time that we talk about smoothness at a point, singularity at a point, or equation at a point, what we are talking about are properties of this smooth chart U. So actually, when the automorphisms are finite, which means that which means if you want that we are dealing with a Deligne-Mumford stack, but we won't care about the name either. In this case, this chart U can be chosen to be étale, and this tells us that we will not have to worry about stackiness issues, not even when we want to compute the dimension. Let me remark that it is important to keep in mind this automorphism when you want to study the intersection theory of these spaces and when you really want to compute some invariance. But for what we want to do in this series of talks, which is just to understand the local structure, for us is enough to work on these charts, which are schemes. Okay. So this is, I think I have 5 minutes left, or even if I don't, I'll take them. Do I have 5 minutes still?
Yeah, you've got plenty of time, don't worry.
Okay, very good. Okay, so we have now, we have seen everything we wanted to see about the formation of C. Of a nodal C, and about this space of pre-stable curve. Let's now see what happens if together with our curve C, we also want to deform a line bundle. First of all, let's try to deform the line bundle, leaving the curves fixed. So we want to study the deformation of L, which leaves C fixed, which means that for C, we take the trivial deformation C times the epsilon. And statement, these deformations are parameterized by the H1 of the structure sheaf of our curve, and the obstruction are contained in this H2, thus there are no obstruction for dimension reason. And finally, the infinitesimal automorphism are given by the H0 of the structure sheaf. I mean, in this case, actually, it's easy to describe. We know the automorphism of L is just a C star, because given a line bundle, we have a C star of automorphism given just by multiplication by a scalar. Okay, and again, let me give a quick idea of how we see that. So we have this set where we have the trivial deformation over the epsilon and a line bundle over it, which in order to be a deformation, it has to be flat over the epsilon, and it has to reduce to the line bundle straight L once we restrict to epsilon equals 0. Then let us look at this sequence. And let's consider this sequence tensored by L. Since L is flat over the epsilon, tensoring will keep exactness on the left. And so this is associating to a deformation L, an element in the X1C of L with itself, but it is nothing but our H1 COC. And vice versa, given an element in this X1, we can define an action of epsilon on the middle guy of the extension, which is what gives us a deformation over C times the epsilon. And again, having studied deformation, we can now describe the Picard stack, which is the stack that parameterizes the curve together with the line bundle. And having studied deformation with a fixed curve is telling us something about the forgetful map which target the pre-stable curves. It's telling us that this map is smooth of dimension G-1, which is the dimension of H1 COC minus the dimension of the automorphism. And so we have that this Picard stack itself is smooth, and the S dimension just given by the dimension of the base plus the dimension of the fiber. And finally, in order to understand dimension the regularity of the modular space of maps, what we'll have to do is study this map here, which forget the section. But and we will see tomorrow how to do that. And this finally is gonna complete the study of the local structure of the modular space of maps to projective space.